Okay, so we're looking at different condition of this vibration modes, free vibration of a spring mass system, and also we've seen forced vibration of a spring mass system without damping, but with a forcing force. In the free vibration case, we don't have the constantly acting force on the mass, but in the forced vibration, we have constantly acting force, but no damping. In the third case was a free vibration of the spring mass damper system, which means we have initial disturbance to initiate the motion, then it's a free vibration throughout. And the last and the most complete, most practical case is where you have a spring mass damper system. Spring and damping system is representing the soil or any material for vibration. But in our case, usually we're dealing with geotechnical problems. So that's why you see it. It's spring is and damping is representing our soil. And the block is a foundation and the constant force acting on it, causing the vibration is something like a machine foundation. Or this is also similar to an earthquake. It can be an earthquake or it can be a machine foundation. In this case, it's like general. And we have seen the detail of this, what their vibration solution look like, the time history responses, the amplitudes. And we derived the most fundamental equations where the natural circular frequency square root of k by m, or the period of the motion is 2 by wn. Wn is 2 pi fn in terms of frequency, or the frequency you can find is 1 over 2 pi square root of k by m, or the period is just the inverse of this 2 pi square root of m by k. Or you can derive this equation in terms of the initial static displacement. And a forced vibration also we have seen only with the spring without damping, and derived from the main general equation. And we have seen what resonance is. When the motion amplification factor, especially when the frequency ratio, W by Wn square, or W by N is when it is close to 1, we have infinity of amplitude of motion. The two W's, W is the forcing frequency on the foundation. It can be an earthquake or a machine vibration, but Wn is the system frequency, the soil natural frequency with the foundation. So we can calculate this. So we have seen how resonance, progressively with time, the amplitude increases, and at some point it results into failure. In the most complex system with a free vibration, spring, damper, and mass system, we can have three kinds: over damping case, critically damping case, and under damping case. The most natural case for our geotechnical properties is the blue one, the under damping case. But the other ones you'll find it in, especially in fluid dynamics, hydraulic systems where the damping is much larger. But in soil case, soil damping is about 10, 15, 20%, depending on the density and the type of soil. Structures, for example, concrete, about 5%, 7% damping, depending on, if you are considering cracks, it can be as high as 10%. So usually the blue line is the most representative for civil structures, which is the under damping case. So these are the cases: over damping condition where damping ratio is greater than 1. Case 2, critically damping condition with the damping ratio is equal to 1. And the most practical case for our case 3 is under damped condition where the damping ratio is less than 1. So in this case, We have seen the solution for all three, especially derived from the main general equation of motion. Main general equation of motion, we have it, the inertial component mass times velocity, mass times acceleration, plus damping times velocity, plus the stiffness component, stiffness times displacement equals to 0. And from there, we have seen this general equation of motion. And depending on this, what is under the square root, we have these three cases: over damped case, critical damping case, and under damping case. And we define the damping ratio to be the damping by the critical damping. Critical damping 2 square root of km. And depending on that, then you have over damping condition, which is the green line. This is like a sample plot. As if you plot amplitude versus time, this is what you'd get. Critical damping case or over damping case, they don't go into oscillation. They damp out very quick without much oscillation. And you have this general solutions for the displacement versus time. Everything else is constant. The damping ratio is constant, the initial velocity, initial displacement, and Wn even it's constant because it's the system property. From lab tests or field tests, you can determine the stiffness of the soil and the mass of the block, then you can compute Wn. So if you plot displacement with time, you have this equation for over damping condition, which is, in this case, is the over damping condition, which is the number 1. For number 2, case 2, critically damping condition, which is the red line. You have a solution of like this Z equals in terms of the initial displacement, initial velocity, system frequency, and time. And for case 3, and the last is the most practical one, under damping condition D, when the damping ratio is less than 1. We're talking like 15%, 10% for soil. In that case, we have this displacement time equation, and that one is the one with the blue one. If you have to focus in one thing, the case 3 is the most practical for our case. And if you're interested in the derivation of these equations, they get into complexity for the class, but I put the links here. See derivation in reference to section 2.5. You can look at them, how they arrived to these equations. It's already derived. In our case, as engineers, we usually use them. We use it, we put it into practice. So we're not much interested into how it is obtained or deriving it again. So that's why I didn't put any detailed derivation here, but you can look at these sections if you need it. And I'm not expecting, like I said before, I'm not expecting anybody to memorize long equations like this, but be aware of what it means, what each terms are, and how the characteristic it is. And if you are asked to solve a problem, you'll always be provided with the equations. So under damped condition with D less than 1, we know that this is a displacement equation with time, and this equation can be simplified further. Let's see. Let me pick my favorite. Okay. So this equation can be simplified further into this form. Z is equal to Z, capital Z, cosine of Wt minus alpha, where you have a sine cosine function with Z in front of it. That's usually the amplitude. If you have the cosine plot, let's say if this is a time history plot, then the Z, the capital Z, is always the amplitude. That's what it tells you. So if you see any cosine or sine equation with some constant in front of it, that's usually the amplitude. And the cosine component, it's telling you how it is varying with time. It's telling you how the vibration is occurring. But in terms of the maximum value or the amplitude, it's usually that coefficient. So that Z, the amplitude, it's given by this equation. Exponentially decaying amplitude. Yeah, in this case, it's not like constant amplitude, but it's decaying with time because it's dying, because we have damping in it. So it's getting smaller and smaller and finally disappears. So that's why you see it with time, it varies with time because of the damping. If there was no damping, it would remain constant amplitude. But if you have damping, it decreases. And because of the damping, also the natural frequency. So you have Z defined with this equation in terms of all these constants: the initial velocity, the initial displacement, system frequency, the damping ratio, and alpha, the phase angle, is also given by this constant. That's a constant value. It's depending on how it's shifting. It has a phase shift initially. And also WD in these equations, it's a damped natural frequency, a damped circular natural frequency. We know that Wn, the undamped case, is the one we defined before. Let me put that side by side so you can see it clearly what it means. Yeah, this Wn was undamped natural frequency that we defined. Now, when we have damping, it varies slightly. And that variation is what you see in this one, Wd. E is equals to Wn square root of 1 minus t squared. So the damping is affecting it. So that's one observation you should take away. The dampened natural frequency is slightly less than from the undampened natural frequency Wn by square root of 1 minus d squared. D is the damping ratio. If there is no damping, the damping ratio would be 1. This would be 0. If there is no damping, D will be 0. So this will be Wd equals to Wn. But if you have damping, this will reduce it a little bit. But Wd is somehow a little bit less than Wn. So when you have a damping case, even the natural frequency is affected a little bit. So make sure to memorize these simple equations and what they mean. And we have logarithmic decrement. Logarithmic decrement, it's nothing but we have decreasing amplitude. If you see the damped vibration, especially in the blue line, this one, the under damping case, we know that the amplitude is gradually decreasing and disappearing. And that's where we talk about logarithmic decrement. It's gradually decreasing. If you consider this is one period from peak to peak, that's a damped period because we have the damped natural frequency. So, and the amplitudes are also decreasing. So if you divide two successive amplitudes, let's say in the next cycle we have Zn plus 1 cycle compared to the Zn. If you compare the two amplitude Zn plus 1 by Zn, you have these expressions. These expressions is coming from the previous equation. Z is given by this, which is the amplitude. So we are just dividing the two equations because this big term under the square root, it's constant, so they cancel out. So what you have is this exponential component only. Exponent minus dWnt. So if you divide the two between two amplitudes, this is what you'd get. Minus dWn Tn plus 1 at Tn plus 1 the amplitude compared to the amplitude at Tn, which means these two amplitudes, the ratio of these two amplitudes. Then which means exponent of this Tn plus 1 minus Tn times minus dWn. But Tn plus 1 minus Tn, what is this? This is just a period. The Tn plus 1 minus the Tn is the period, which is this. But the period, we know that is 2 pi by WD. W is a damped circular frequency. And you can represent it with what we calculated before, Wn square root of 1 minus d square. So if we know the period, and if we plug it in back in the main equation, then you'll end up finally finding equation like this for logarithmic decrement. So the logarithmic decrement between two successive amplitudes, you can find it finally as 2 pi d square root of 1 minus d square. It's just all the function of the damping ratio. So the difference between the two amplitudes is finally the difference between, just in terms of the damping ratio. Or if the damping is too small, it can even be simplified as 2 pi d. These equations help us. Why we do this is it finally helps us to calculate damping. If you don't know, for example, the damping of the soil, you can actually do a free vibration test, get two amplitudes anywhere, can be between these two, the first one and second one, or anywhere you can measure. Two amplitudes. So measure, then you can actually find the D. That's where it's practical. So you can calculate the damping ratio. We will see how to calculate the damping values of different materials at some point, but this is one main concept we use to determine damping ratios. Let's see an example where we have a machine foundation with a given weight of 60 kilonewton and a spring constant of 11,000 kilonewton per meter. For now, assume we did a field test and we know the spring constant of the soil, and it's 11,000 kilonewton per meter. And also assume we know the damping of the soil as 200 kilonewton second per meter. And now determine whether the system is over-damped, under-damped, or critically damped condition. For that, what you can do is find, first of all, the critical damping ratio. We know that critical damping, you can calculate it 2 square root of km, and let's say you found this value. If you know the critical damping, then compare it against the value of the damping you're given, or find the ratio. And when you find the ratio, that's the damping ratio, D, capital D. And for that, we get 0.386, which is less than 1. If it is less than 1, then which means it is under damped condition. And the second one is find the logarithmic decrement. The logarithmic decrement, we know that we just talked about it. We have logarithmic decrement is 2 pi d by square root of 1 minus d square. We're asked just to find the logarithmic decrement, knowing the damping ratio. Once you find the damping ratio, then logarithmic decrement is just in terms of the damping ratio, 2 pi d over square root of 1 minus d square. Then we found 2.63. So that's the difference between two successive amplitudes. Then find the ratio of two successive amplitudes, which is just the exponential of the logarithmic decrement. Zn by Zn plus 1 is the exponential of that logarithmic decrement to determine. Then it's 13.87. So which means if you have two amplitudes, then the difference between two is, this is exactly it. So amplitudes are dying out, let's say. So this is the difference between the two is around 13.87. And finally, determine the damped natural frequency. The undamped natural frequency, you can calculate 1 over 2 pi square root of km. And the damped is just, you know, it's reduced by square root of 1 minus d square. We just talked about it. So you can compare the damped natural frequency versus the undamped natural frequency. Damping is affecting or reducing the frequency a little bit, not significantly. It just shifted from 6.75 to 6.23. But you can see the impact of damping. And the final case is a forced vibration, which is a fourth case. A forced vibration of a spring mass damper system for a steady state condition. This is the most practical case. You have your soil represented by a stiffness K and damping C. and you have a mass of the foundation and also the mass of the equipment on it or the input motion. Now, if you have a complex system like this, initially when you apply the input motion, you may have some noise, a transient, very short duration motion, and it may be irregular. But after a while, the pattern of the displacement is like you'll have smooth cyclic motion. And we call that smooth motion steady state. Amplitudes vary because you have damping value, but it is a smooth damping out. It's not like the initial. The initial noise is usually attributed to, for example, initially when you apply the force initially, you may have loose particles. You may have, insignificant amount of settlements or particle rearranging before you find some elastic response. So that initial noisy part is what we call transient. And we don't usually model this one. It's initial, it's very short duration, but the steady state, once you have a perfectly elastic response, that's we are talking in this section, which is a steady state motion. So for this, similar to the other three sections we have seen, we have the general equation of motion, the mass times acceleration, stiff damping times velocity, and stiffness times displacement, or the inertial force, the damping force, and the stiffness force. The sum of all these three should be what's applied on the machine foundation in this case, the input motion, which is Q naught sine omega t. Q naught is that amplitude. Sine omega t is depending on how it's behaving. You have the input motion, which is cyclic, like a sine wave, but Q naught is the amplitude. If you have such a section, the solution for this steady state motion is, then it can be represented by Z equal to capital Z cosine of omega t plus alpha. This is just the equation of the solution of this general equation of motion with all damping, with these input motions, constantly applied input motion, and the detailed derivation of this solution, you can still find it in reference to section 2.7. When you need it, or if you are interested to it, just feel free, go ahead and look at it. And you'll see how they arrived into this compressed form of equation. So Z capital Z, which is the amplitude, is given by in terms of the amplitude force, Q naught, by K, the stiffness of the soil, a frequency ratio, and damping ratio. And the alpha, the phase angle, is also constant, is given by the frequency ratio and damping ratio. We're more interested in the final outcomes, but feel free to look at how they derived it, so you have a feel of it. Now, for non-dimensional plot of amplitude, let's say if we put Z divided by Q naught by K, so which means 1 over this term. If we plot that for different damping values, versus the frequency ratio, these are the plots you would find for different damping values. For D equals to 0, which means there is no damping, you have almost infinity of motion. You can see it in this equation also. If you put damping equals to 0, see it, damping equals to 0, this term is 0. All you have is this term, 1 minus the frequency ratio. And in the frequency ratio, if W equals to Wn, see it, at this W is equal to Wn, which is 1, which is a resonance case for damping equals to 0. You will have almost infinity of motion. The damping is equal to 0. We put it up to a plot of 5, but that thing goes to almost infinity. That's more unrealistic because in reality, we have some damping value. For example, soil, we know that we have 10, 15, 20, 30% of damping. So the most practical plot is that, damping ratio of 10%, you have this one. 20%, you have this one. 30%, which is 0.3, you have this one. 40%, 50%, 60%, you have all these values. So if you plot that, there is some observation you can make. The maximum value of the amplitude If damping is not equals to 0, you'll see the peaks slightly to the left of the frequency chart or the frequency value of 1. If there is damping, the peak values are not happening at W equals to Wn. That's one takeaway. If damping equals to 0, the peak value is at 1.0 and that one is infinity. But that's more ideal case because practically we have damping. And for other cases, if it is very small damping, like 1%, 0.1%, is very close to a value of the peak value is very close to a frequency ratio of 1. But when you have larger damping values, then the peaks are happening at a smaller frequency ratio. So from non-dimensional plot of amplitude, it can be seen that maximum amplitude doesn't occur at resonance, W equals to Wn, as it occurs in the case of forced vibration for mass spring system. If there is no damping, if it's only mass spring system, we have seen the peaks is equal to 1.0. But when you have damping, the peak values are away from the W is equal to Wn. The smaller the damping ratio values, the maximum amplitude occurs closer to the resonance frequency. Yeah. Which means when damping is smaller, it gets close to a frequency ratio of 1 where the peak is occurring. And the maximum amplitude for a spring mass damper system, we have this equation. This is a non-dimensional plot we just plotted in the previous page. This is the equation for this. For maximum value of this, we're trying to find where the peaks are occurring. If the peaks are not occurring for a damping case, it's not occurring at W is equal to Wn, or which is 1.0, then where are they occurring? Let's say a 40% damping. 40% damping is occurring right here. Then what's the frequency ratio? We want to determine that. So if you know the equation of a graph, and the maximum value, the way you find it is find where the slope is 0. The slope, for example, for this curve, slope is just the first derivative of this with this. And if the slope is 0, which means it's a horizontal line. So if you take the first derivative with a frequency ratio plot, this, and equals to 0, which is a horizontal line or the maximum value, and solve this equation, you'll find then W and Wn giving you equation which is W is equal to Wn squared 1 minus 2d squared. So W by Wn, it's really giving you this with a damping ratio value. Fm is the frequency at maximum amplitude, which is because our interest is to find where the peak value in each curve, each different damping values are occurring. Then you can find that specific frequency where it is occurring. If you know the frequency where it is exactly occurring, then the max amplitude at resonance, which is this peak value for 40% case, you can find it with this equation. So you know where it is exactly occurring in terms of frequency. And once you know that, you know the curve, so you know the peak value where it's occurring. That leads us to a point where what is the maximum dynamic force transmitted to the subgrade? That's more our interest as a geotechnical engineer. If we know these motion properties, if we know the solution of this equation, then our interest is, okay, what is the maximum force from this machine foundation vibration going to the subgrade? Because finally, what we want to determine is how much settlement we have, how much bearing capacity the soil have. So we should know how much force is passing. And that maximum force, we know that these peak values, it's helping us to find the maximum force passing to the subgrade. So for vibrating foundations, it's sometimes necessary to determine the dynamic force transmitted to the foundation. This can be given by summing the spring force and the damping force caused by relative motion between the mass and the dashpot. When we have a spring only without damping, the force transmitted to the subgrade, it was only a spring force. But now we have damping, which is damping out also the motion. It's somehow helping. If it's a spring, Any force acting here, it's passing to the ground also. But now damping through its hydraulic system is also helping to reduce the motion. So the way we find it is we have our general equation of motion. We know the solution of this general equation of motion, compressed form. Max dynamic force on the subgrade, it's the stiffness force and the damping force. The max dynamic force is the force transmitted from the stiffness plus the force transmitted from the damping. When in the case of damping, it's helping. It's resisting some of the, or damping out some of the motion going to the soil. So if we know the displacement solution for the general equation of motion, K times Z, the stiffness force, is just the stiffness of the soil times Z. We know Z at any time. For damping case, the damping force is what? It's C times the velocity. But the velocity is, since we know the displacement, you can take the first derivative. If you know the velocity displacement history, then the velocity is just the first derivative. First derivative of this is Z cos omega t plus alpha. It's minus cosine will be minus sine. W will come out as a constant, so you'll have minus WZ sine omega t plus alpha. This is a velocity, or it's just Z dot is just the first derivative. It's dz by dt. Once you know the velocity, then the max dynamic force is the stiffness force plus the damping force. Now the damping force, you can see it, it's minus. It makes sense. Why it's minus? Because the damping is always trying to help you reduce the force. If you further simplify this equation, you'll arrive to the dynamic force, the maximum dynamic force from this system going to the subgrade is equal to Z, which is the amplitude of motion, the square root of K squared, which is stiffness square, plus damping, the forcing frequency square. This is just the final outcome. You can see the derivation of this equation in this section, reference to section 2.6. Now, Z is the amplitude. Even if we simplify it here, it's actually this is the equation for Z. Q naught K, if you take it the other side, this whole thing is D. Or in the previous page, we have it here. Z equals to Q naught by K square root of this whole term. So everything is known. So if you know a spring mass damper system with a constant cyclic force acting on it, then you can find the maximum force going to the subgrade. As a geotechnical engineer, you need this. Then because you need to find out what is the maximum force and how you can design your settlement and your bearing capacity. Let's see an example. This is an example taken from reference to a machine and its foundation weigh 140 kilonewton. That's the weight of this. The block, the machine foundation plus the machine itself is 140 kilonewton. The spring constant and the damping ratio of the soil supporting the soil may be taken as 120,000 kilonewton per meter, and 0.2 is a damping ratio. Forced vibration of the foundation is caused by a force that can be expressed as, this is a cyclic force acting on the foundation, Q naught sine omega t. Its maximum amplitude is Q naught, which is 46 kilonewton. Sine omega t is just making it to oscillate. And omega, forcing circular frequency is 157 rad per second. And damping ratio, you have 0.2, which is under damping condition, right? Because when D is less than 1, which is the most practical case for civil engineering, that's under damping case. Now, these are all the given. But you're asked to determine the undamped natural frequency of the foundation. We know how to find the natural frequency, the undamped case and undamped case. So the undamped case is 1 over 2 pi square root K by M, which is no damping impact on it. So natural frequency without damping is 14.59. This is hertz. The unit is missing here, or 1/second, or it's in hertz. B, find the amplitude of motion. The amplitude of motion, we know that the equation that I showed you before, this is the equation. This is the plot we have been plotting. The amplitude of motion is Q naught by K over square root of 1 minus the frequency ratio squared, the whole thing squared, plus 4d squared, the frequency ratio squared. Wn is 2 pi fn, circular frequency. You can calculate it because you have the natural frequency calculated. And the forcing frequency is already given. Forcing frequency, where did I see it? 157. Here it is. This is a forcing frequency. The forcing frequency is from the machine, which is W right here. Wn is a system frequency, the soil. So if you put together everything, then the amplitude of motion for this case, you'll find it 0.187 millimeter. It looks very small, but this is vibration. When repeatedly you have this amplitude of motion, it can cause damage. For a static problem, probably this is insignificant because you have a one-time just settlement 0.187, it's nothing. But for continuously vibrating thing, it can grow. It can cause damage. And the third case is find the maximum dynamic force transmitted to the subgrade. The maximum force going from the machine foundation through the block, through the spring and damping, finally to the soil is, we know that it's given by Z, the amplitude of motion, square root of K squared plus the damping ratio, the damping of the soil, forcing frequency squared. But the damping of the soil, you can calculate it from the critical damping and the damping ratio given. Damping ratio 0.2 is given. Damping ratio 0.2 given previous page right here. 2d square root of K by. Then if you plug all the numbers, you'll find damping value of 523 kilonewton second per meter. And finally, the dynamic force is going to the soil is 27.2 kilonewton. Now, there are more things here. In the example, it's not included. This is just a dynamic component. On top of this, you will have the static component, the weight. So the maximum force acting on the soil is W plus or minus the dynamic component. So in your design, this is what you use. In the worst case, you'll have W, the weight of the foundation and the machine, plus the dynamic component. In the least case, you'll have the minus that probably doesn't govern. So that completes these 4 sections. Now let's come to some general terms. The 4 sections we divide are just with a spring with a spring, and with force and without force, with damping and damping spring, with force and without force. So these 4 cases, but the last one is the most practical case for our case. Now let's see some additional terms. Force transmissibility and vibration isolation, or base isolation. This is very useful concept in civil engineering, both for geotechnical and structural engineers. So you'll find this section in reference 6, section 3.5. It's not well covered in reference to the Braja Emdas book or the Kramer book reference 1, but reference 6 has a detailed coverage on it, and it's very useful concept. Force transmissibility, or it's usually represented by TR. TR is a maximum force transfer to the ground. That's F dynamic we just computed. We have seen an example on it. The maximum dynamic force transmitted to the ground divided by the maximum applied force to the mass. The maximum applied force to the mass is the Q naught. If you have a machine vibration like this, Q naught sine omega t, Q naught, we know that this is amplitude the force amplitude. This is the maximum value from this sine function. So the maximum dynamic force, F dynamic divided by Q naught, is what we call force transmissibility. That will help us to understand it and to reduce how much force is going. The maxi dynamic force, we just derived that, is given by Z, the amplitude of motion, square root of K squared plus CW squared, where D is equal to damping ratio, C by CC. So C you can calculate from the damping ratio in case of damping ratio. One of them is enough, either if they give you damping value or the damping ratio with the mass and stiffness. Z, we know that Z from the previous equation, it can be found from the steady state solution, which is this form. It's a simple form. The maximum value of the force applied, the stiffness of the soil, the frequency ratio. Frequency ratio is a forcing frequency divided by the natural frequency of the system, the soil, plus 4 the damping ratio squared and the frequency ratio squared. So we have this general equation of motion. This is the last case we have been discussing: spring, damper, mass, and a constant force acting on it. Constant cyclic force causing the vibration. So if we know Z, if we know the dynamic force is given by this equation, and if we know Q naught, if you put all this together, then the transmissibility ratio, TR, you will find it this simplified form. 1 plus in bracket 2D frequency ratio, the whole squared, divided by 1 minus the frequency ratio squared, the squared plus 1 plus this whole thing. So everything is known. Frequency ratio is known, damping ratio is known. So it's damping ratio and the frequency ratio basically. So let's see the plot of that transmissibility plot. Transmissibility TR versus frequency ratio. We know the equation. Then if you take W by Wn as a variable and plot it for different values of damping, this is what you observe. So the peak values, they are around the frequency ratio of 1, of course, close to the resonance. Because of damping, they are shifting a little bit to the left. And now, see, as the damping value is smaller, then the peak value of the transmissibility ratio is high also. The less damping, the more force passing to the soil. But that is true only up to a frequency ratio of square root of 2. If you see it as square root of 2, everything is just coming to a common point. Transmissibility ratio, if it is 1, we know that transmissibility ratio it's the dynamic force passing to the soil, the maximum dynamic, divided by the Q naught, the maximum applied force, right? If it is 1, then the two are equal. The max applied is equal to the max dynamic force passing. If you see it for a frequency ratio of less than square root of 2, for all these values, it's more than 1. Transmissibility ratio is more than 1, which means we're having more force passing to the soil. If you see it beyond square root of 2, it's telling us it's less than 1. The force passing the soil is less than the applied force on the mass. So you can see this. This plot is equivalently applicable, whether it's a machine foundation where you have like a sine function load or a ground motion like an earthquake. In both cases, if you have a spring mass system, this is the characteristic, how the maximum force is passing. For a frequency ratio less than 2, we have a larger force passing to the soil. For a frequency ratio greater than 2, we have less force passing into the soil. This is what we want in our design, because we want less force to pass to the soil. So by design, what we learn from this chart is it's telling us to design our system or to select our WN, W, which is a forcing frequency, or to design WN, the system frequency, so that the vibration occurs above square root of 2. This is what we want. If the vibration occurs at 1, here, this is the maximum damage you have. Remember what Mexico earthquake did. Because the vibration occurs at a resonance, so many buildings collapsed, which have a frequency of around this range. But in our design, what we can do, we can shift our frequency. We can be away from this area, especially in this area, because we have less force passing to the soil. That's what this transmissible ratio is telling you. When you design your mass spring system, your foundation system, make sure you design it beyond the square root of 2. Why? Because we want the maximum dynamic force to be less than the applied force. If we see it, if we do it here, there are many things. It can be resonance around this area. Around this area is the maximum force you'll have. You see these peaks. No matter how large damping you use, still you have significantly large force passing. If you are at a low frequency, you may not find the product you want. Especially a machine, they may not run at this frequency because they are not productive. They may have to run at higher frequency. But if you choose that higher frequency within this range, it's destructive. But you can go even much higher and reduce the dynamic force. So that's the takeaway from this. So let's go through this write-up. Damping always decreases amplitude of motion, but it decreases the transmitter force only if W by Wn is greater than 2. Damping is always advantageous. It reduces the force. You can even at the peak value, at a frequency ratio of 1, you can see it. A damping of 1% is higher than a damping of 5%. 10% give you less, 20% give you much less, 70% give you much less. Damping is always good. It reduces the motion or the force transmitter. However, the force transmitter would be significantly less if it is greater than square root of 2. The dynamic would be force transmitter would be less only if your frequency ratio is within this range. That's what this statement is saying. Most rotating machines are designed to work at W by Wn greater than 2. Of course, they are designed to work in this range because we want less dynamic force to pass through. So we avoid crack, we avoid excessive settlement or bearing capacity failure. However, when they start, they gradually increase their speed to reach to the operating frequency and pass through resonance, causing large transmitter force. Large damping is used to reduce the force at resonance. Now, when you start a motor, they don't jump and reach to a frequency of this value immediately. It's a progressive. They increase the rotational speed, increase, and finally they go through, even they pass through the resonance. They have to pass through the resonance frequency to reach to a frequency of this value. It's like the speed is increasing. At some point, while that motor is working, you will see it a higher vibration motion at some point. That's a resonance point. But once you pass that, that's a short duration. When it is increasing, it's like instant motion. So you don't keep it there. It's constantly increasing. You'll see a higher vibration at some point. Then it goes higher and quietly works in this area. But it passes through that resonance motion. In that resonance motion, there are two things happening. One, we use still larger damping value to reduce still the maximum force when it passes through that frequency. Even if it is short duration, we still want to damp out more. So we still use larger damping value so that when it passes through that resonance frequency to go to the higher frequency, we don't have significant impact. So that's what this second paragraph is saying. Now, the way you achieve that, there are so many things. Now, W and Wn. W, you may not have a control. W is a forcing frequency. It comes from the manufacturer, or it comes from nature in case of earthquake. They just provide you. Let's say if there is a turbine or a motor or some generator, W comes from the manufacturer. But you have a control on WN. WN is a system frequency. That's the natural frequency of the soil. So by making the soil softer or stiffer, you can control this W by WN. That's how you design it. WN is under your control as a geotechnical engineer. Loose soil corner, you can represent it by, stiffer soil. Clay replace it by a sand or a well-mixed sand and gravel. Stiffer ልታረጉት ትችላላችሁ. So you have a control in this W by WN. As WN decreases, WN decrease ስታደርጉ, you can achieve this area. To make W by WN larger, you can decrease WN. But decrease ስታደርጉ, what you're doing is you're making this softer. You can make it softer and arrive to this area. But the problem is if you make it too soft, the transmissive force would be small. However, soft spring causes large displacement. You have a large displacement issue. Like if you make it like a clay soil instead of well-graded soil, sand, and gravel, you can achieve this. But the problem is you're going to have a large displacement, large settlement in that case. Or what you can do is you can use something like a rubber to dump out the motion right under the equipment, the vibrating equipment, generator or a turbine or anything. You can use some damper like a rubber material. Rubber is a good material for vibration or base isolation, as it has large damping value and also has less displacement. Now, you can have more practical damper cases in your house. You may have a washing machine. Under the washing machine, you'll see rubber pads. Rubber pads sitting just between the concrete floor and the bolts or the legs supporting the washing machine. What this rubber is doing is actually it's damping out the vibration of this machine. You can buy these rubbers and put it under any vibrating thing you have in your house. Or you can have even bolts made with rubber materials to damp out motions. So you can have various kinds of dampers at different places. All they do is they damp out the motion. They reduce the force to be transmitted. Let's say this equipment, this is like a motor or a generator or anything. When it vibrates, there are forces passing to the floor. So you can see these vibration isolations. You have rubber-made materials or a pad, isolation pad. All this pad and vibration materials, all they do is they isolate whatever vibration you have from this equipment, they dump it out. So it doesn't transfer to the floor or the concrete or the foundation. In case of buildings, those are for equipments. If you see it in case of buildings, what it means is you may have something called base isolation. You have a big buildings founded on rubbers to give it some flexibility at the base. It's like seismic base isolation under building. This is like right on the foundation. It's industrially made, high stiff material, but it gives some flexibility compared to concrete. So what it does is, let's say you have a ground motion like this. What it does is, if you don't have any base isolation, the way the building deforms is like this. See it in one cyclic phase. When it bends, because the foundation is rigid, then you have large bending on this one, because the building is trying to cantileverly bend. So this is back-end force motion. But if you see it in one instant, you have this bending causing a large force on the frames at the bottom especially. So you can develop maximum bending moment, maximum shear, and probably breaking at this frame, at these columns. If you have base isolation, some flexibility built in at the base like this, then see how it behaves. Because of that flexibility, the entire building is moving like a rigid object. So you don't see bending because the bending happens in the base isolation. It's designed for it. You don't see large strain, large bending, large maximum moments at the bottom columns. So that's the difference between when you have a base isolation, building with base isolation, and without base isolation. So you have some examples, like example of buildings with base isolation. For example, Apple's new headquarters in Cupertino, California, has 4-story above and 4-story below, and it's sitting on 700 base isolators. It's in California. California is a high seismic area. We have seen it in chapter 1. So to protect it from any potential earthquake damage, they built it on base isolators. So the entire building will be moving together. No large strain, no large break or shears or bending moments are expected. Or in Japan, this is very common. In Shanghai Season Terrace, Tokyo, Japan, an office building rests on several base isolators. They are very tall, maybe 100 stories or 50-story buildings. When earthquake comes, they just move slowly. So no large strain, no damage is expected. So this is a big concept for geotechnical and structural engineers to apply, to use base isolators. And this base isolator concept, it comes from force transferability. This is a concept holding it. Okay, it's 8:20. Let's have a 15-minute break, and let's meet at 8:30, and we'll do 1 hour, and we'll probably finish this chapter.